To make just 1 ton of pure aluminum, something light enough to build an airplane wing, the industry has to deal with millions of tons of a toxic, caustic waste byproduct called red mud. It's radioactive in trace amounts. It's corrosive enough to burn skin on contact. And right now, billions of tons of it sit in massive waste ponds around the world. Today, we're going to show you exactly why. Aluminum feels clean, lightweight, shiny, recyclable. It's in your soda cans, your phone, your car. But almost nobody thinks about where it actually comes from, or what gets left behind in the process of making it. What you're about to see is the real story. How raw bauxite ore gets transformed into pure aluminum, and exactly why that transformation produces a toxic, caustic byproduct at a scale most people can't even picture. Coming up, we're breaking down the entire refining process step by step. But there's one specific part of this system that the aluminum industry has been trying to solve for over a century, with no perfect solution yet found. We'll get there. Let's start from the beginning. Let's start with the raw material, because this is where the entire problem actually begins. Aluminum doesn't exist in nature as a shiny metal. It exists locked inside a rock called bauxite, a reddish-brown ore mined primarily in countries like Australia, China, Guinea, and Brazil. And here's the first thing that surprises people. Bauxite itself isn't dangerous. It's not toxic. It's not radioactive in any meaningful sense. It's just rock, full of aluminum oxide, mixed in with iron, silica, and other minerals. The danger doesn't come from the rock. It comes from what has to happen to that rock to pull the aluminum out of it. Bauxite mining happens at a massive scale. Open-pit operations strip away topsoil and vegetation, exposing the ore underneath, which gets excavated using heavy machinery and loaded onto trucks or conveyor systems for transport. This stage alone reshapes landscapes. Bauxite mining regions, particularly in tropical areas, often sit on top of rainforest or agricultural land, which means extraction comes with environmental trade-offs before the ore has even left the ground. But this is just the beginning of the story, not the main event. The real transformation, and the real problem, happens after the ore reaches a refinery. Once bauxite arrives at the refinery, it goes through something called the Bayer process, named after the chemist who developed it back in 1888. And still, remarkably, the primary method used by refineries worldwide today. Here's how it works. Broken down simply, crushed bauxite gets mixed with a hot, highly concentrated sodium hydroxide solution. Essentially, industrial strength lye. Under high temperature and pressure, this solution dissolves the aluminum oxide out of the rock, separating it from everything else inside the ore. This is the critical moment. The aluminum oxide, the valuable part, dissolves into the liquid solution. Everything else, iron oxide, silica, titanium dioxide, unreacted minerals, and leftover caustic chemicals, does not dissolve. It stays behind as a solid, thick, reddish slurry. That leftover slurry is red mud. Here's where the real problem starts to take shape, and where you start to understand exactly why this material has plagued the aluminum industry for over a century. Red mud isn't just leftover dirt. It's a complex mixture of heavy metals, residual caustic chemicals, and fine particulates with a pH level around 13. That's almost as caustic as drain cleaner. It can burn skin on contact. It can contaminate groundwater if it leaches improperly. And in some bauxite sources, it contains naturally occurring radioactive elements like uranium and thorium, concentrated during the refining process into levels that require careful handling and monitoring. And the volume is staggering. For every single ton of aluminum eventually produced, the refining process generates somewhere between 2 and 4 tons of red mud, sometimes more, depending on the quality of bauxite being processed. Multiply that across global aluminum production, and you get a truly overwhelming number. Somewhere around 150 to 200 million tons of red mud generated worldwide every single year. And here's the part that makes this genuinely difficult to solve. Red mud doesn't disappear. It doesn't break down naturally. It doesn't get neutralized over time on its own. Once it's produced, it has to go somewhere, and it stays there, essentially forever, unless something is actively done about it. Right now, there are over 3 billion tons of accumulated red mud sitting in storage ponds and waste facilities around the world. 3 billion tons. And that number grows every single year, because right now, there's still no large-scale solution that consumes red mud faster than the aluminum industry produces it. So how do refineries actually handle this? How do you manage a toxic caustic byproduct at a scale this massive, without it becoming an environmental catastrophe? For most of the last century, the answer has simply been storage. Refineries build massive containment areas, often called red mud ponds, or bauxite residue storage facilities, where the slurry gets pumped and allowed to settle. These aren't small holding tanks. Some of these storage facilities span hundreds of acres, with walls and dikes engineered to contain the material and prevent it from leaching into surrounding soil or water systems. As more red mud gets added over time, the walls have to be raised higher. The facility expanded, the engineering scaled up to match the ever-growing volume. And this is where things get genuinely risky. Because if those containment walls ever fail, and there have been catastrophic failures in the past, with red mud spills flooding nearby towns and waterways, the consequences are severe. Caustic, toxic materials spreading across agricultural land, contaminating water supplies, displacing communities. This isn't a hypothetical risk. It's happened before, which is exactly why modern containment engineering has become so much more rigorous than it used to be. Modern facilities use multiple layers of protection: engineered liners, continuous monitoring systems, drainage systems designed to catch any seepage before it reaches groundwater. But even with all of that, storage isn't a permanent fix. It's a way of managing the problem, not solving it. One method refineries use to reduce risk is drying the red mud before long-term storage. Wet red mud, fresh from processing, is genuinely dangerous to handle and transport. It's a thick, caustic slurry. So many facilities use a process where the mud gets spread in thin layers and allowed to dry, either naturally through evaporation or through mechanical drying systems. Once dried, red mud becomes a fine, powdery solid, easier to handle, easier to stack, and somewhat less likely to leach into groundwater if the storage area is engineered correctly. But drying doesn't neutralize the material chemically. It's still caustic. It's still potentially radioactive in trace amounts. It's just easier to physically manage. Some facilities go a step further, attempting to neutralize the alkalinity of the red mud using various chemical treatments before storage, reducing that extreme pH level closer to something less hazardous. This helps, but it adds cost and complexity to every single batch processed, at a scale of millions of tons per year. Here's the part of this story that's genuinely fascinating. Because for over 100 years, researchers and engineers have been trying to find a way to actually use red mud, rather than just storing it indefinitely. And there's good reason to try. Red mud isn't just waste, it still contains valuable materials. Iron oxide makes up a huge percentage of its composition, sometimes as much as 50%. There's titanium dioxide in there, trace amounts of rare earth elements, even residual aluminum that wasn't fully extracted during the Bayer process. Some facilities have started experimenting with recovering iron from red mud, essentially treating it as a low-grade iron ore. Others are researching its use as a raw material in cement and construction materials, since its mineral composition can partially substitute for materials normally mined separately. There's even research into using red mud in steel production through specialized reduction processes that extract usable iron while neutralizing the material's hazardous properties in the process. But here's the honest truth. Right now, none of these solutions operate at a scale anywhere close to matching the amount of red mud being produced. Globally, less than 5% of newly generated red mud gets repurposed into something useful. The other 95% still goes into storage ponds, adding to that ever-growing 3 billion ton stockpile. This is the unsolved problem we mentioned back in the introduction, the one the aluminum industry has been wrestling with for over 100 years. Researchers know what's inside red mud. They know it has potential value. They just haven't found a way to extract that value at industrial scale, fast enough to meaningfully reduce the mountain of waste already sitting in storage worldwide. Global demand for aluminum keeps growing. It's lightweight, it's strong, it's essential for everything from aerospace to electric vehicles to packaging, which means red mud production isn't slowing down. If anything, it's accelerating right alongside it. So every single day, refineries around the world are processing more bauxite, producing more aluminum, and generating more red mud, adding to storage facilities that are already strained, already aging, already facing increased scrutiny from environmental regulators and nearby communities. This is the trade-off sitting underneath one of the most useful metals on the planet, a lightweight, recyclable material that makes modern life easier, built on top of a toxic byproduct that nobody has fully figured out what to do with yet. And once you understand that trade-off, once you understand exactly what it takes to produce something as simple-looking as a sheet of aluminum foil, the real question becomes something much bigger than just chemistry. Here's the question worth sitting with. Every aluminum can, every airplane panel, every piece of foil in your kitchen drawer, all of it carries an invisible cost. Not in dollars, but in tons of caustic, toxic waste sitting in storage ponds around the world, waiting for a solution that still doesn't fully exist. We've gotten remarkably good at extracting aluminum. We still haven't gotten good at dealing with what's left behind. And that's really the story here. Not that aluminum is bad, it's one of the most useful materials humans have ever discovered. The story is that progress almost always leaves something behind. And sometimes, that something is a 3 billion ton problem nobody outside the industry ever thinks about. So the next time you crush an aluminum can, or close an airplane window shade, or fold a piece of foil over a dish, remember what it actually took to make that material exist. Because somewhere, right now, that red mud is still sitting there. Still waiting. Still unsolved. If this kind of the hidden cost behind everyday materials content is what you're here for, hit that like button, subscribe, and stick around. Because what's coming next on this channel is built for exactly the kind of person who watched this all the way through. Drop a comment below. Tell us which material or factory you want us to go inside next. Your suggestion might just become our next video. See you inside the next one.